Welcome to DCL 093 Part 1. I say Part 1 because I don't know where my mind was at thinking I could get 4 topics into one video. But the fact of the matter is we'll do base 10 logs and dB in this episode. And then DCL 093 Part 2, which will be a separate video, will cover the dBm and some simple wavelength calculations. First thing to talk about is the base 10 log or logarithm. This is a mathematical concept. You won't use it often in ham radio or in radio in general, but it's important to at least be exposed to it so you understand the foundational mathematics behind the decibel or the dB. But don't get too hung up on math. Don't worry about it. I'm going to try very hard to show you this as simply as I can. And then toward the end of the video, I'll show you how to use dBs without doing the heavy math. You remember from last time, or from math class, when we raise a base to a power, like if we said 10 to the second power, 10 is the base, and the exponent or power is the 2. So 10 to the second power is 10 times 10. 10 to the fourth power is 10 times 10 4 times. Well, to calculate a log, we kind of go backwards with the concept of the power or exponent. What I mean by that is this. If 10 to the second power is 100, then the base 10 log of 100 is 2. Or the base 10 log of 10 would be 1. Or the base 10 log of 1 is 0. Now, having said what I just said, what do you suppose the base 10 log of 14 is? Clearly, you cannot multiply 10 times itself any number of times and get 14. But mathematically, or in theory mathematically, you can do this. If you punched 14 into a calculator, it's going to give you an answer. Right now we could call the answer n because we don't know what that answer might be. But think about it. If 10 to the first power is 10 and 10 to the second power is 100, then n must be something between 1 and 2, and it must be pretty darn close to 1. Well, if you punch 14 into a calculator and hit the log key, you'll get this number. So the base 10 log of 14 is 1.146. What would the base 10 log of 4 be? Well, it's less than 1, but it's not a negative number. If you punch it into a calculator, 4, and hit the log key, you'll get 0.6. Now, this brings up a topic. We generally round these logs to 1 decimal place, like 0.6 or 0.7. That does introduce a little error, but I'll show you later that we're really not too concerned with the slight error it introduces. So 10 to the 0.6 power is 4. So the base 10 log of 4 is 0.6. Now, why do we even mess with what we call the dB or the decibel? Remember, scientific notation and engineering notation allow you to express really large numbers or really small numbers rather simply and rather conveniently once you learn the notation. Well, the dB does something similar. It lets us represent very large or very small ratios with simple numbers. Now, when I talk next time about dBm, I'll show you how to use dBs to talk about specific quantities, but let's leave that for next time. Okay, so some basics. Again, we're comparing two power levels. Now, there is a formula where you can calculate the dB difference in current or voltage levels, but I'm going to leave that to another video. Right now, for the ham radio exam, I'm more concerned about using dBs to compare power levels. Now, very commonly, dBs are used to express the gain in an antenna or the loss in a cable. Sometimes amplifiers will be rated, they'll say, for this power level you should see this much gain, but they won't tell you exactly how many watts output. You can figure that out on your own, and we'll walk through that in a minute. In every case, when you are calculating a dB loss or gain having to do with power ratios, this is your formula. You step through it step by step. The first thing you're going to do, you'll have two power levels, like you have, say, 1 watt going into an amp and 10 watts coming out. To calculate how much gain the amp has, you'd put 10 up here, 1 down here, divide, that would give you 10. You would take the base 10 log of 10, which is 1. You'd multiply it times 10, which is 10. So you have 10 dB gain in your amplifier. So let's walk through this again. Let's say I have this little amp and they claim that it gives me 10 dB of gain with an input of 4 to 8 watts. I drive it with 5 watts and I get 62 watts out. You can probably already answer the question, does this give you 10 dB gain? But let's pretend we don't know. We'll copy the formula up here just for convenience. Now, let's walk through it. I have 62 watts and 5 watts. I do the division. I take the base 10 log of 12.4 and I multiply that base 10 log by 10. So I have 10.9 dB gain, so the amplifier is better than its specifications. The next thing I do is I go to the store and I buy a 100-foot long cable for my 2-meter antenna at 144 megahertz, and the salesman says I will have 3 dB of loss. So I take the cable home, I put 100 watts into the coax, and out at the antenna I have 25 watts. Is that 3 dB loss? Well, let's walk through the numbers. 100 divided by 25, that's 4. Base 10 log of 4 is 0.6. 10 times that, whoa, I have 6 dB. Did I do the math wrong? No. They sold me crappy cable that doesn't meet the spec. So the first question is it a gain or is it a loss? We're going to use the same formula for gain and loss. And no matter what we're doing, we put the bigger number on top and the smaller number on bottom. That means the formula cannot tell us if we have gain or if we have loss. With the amplifier, I started with 5 watts and ended up with 62. So I had 10.9 dB of something and it was gain. With the cable, I lost almost all my power. So I ended up with less than I started, so my 6 dB was a 6 dB loss. And again, the formula tells you how much change you have. It doesn't tell you if it was gain or loss. That's up to you to decide. Now I want to show you the real power of the dB. Let's say I have an amplifier, I put a watt in, I get 10 watts out. So I have 10 times the power. So my power ratio is 10. I do the math. 10 divided by 1, of course, is 10. The log of 10 is 1. 10 times 1 is 10. So I have 10 dB gain. How many dB of gain do I have if I have 100 times power change? The math shows us I now have 20 dB of gain. Another way to do the math is to say I went from 1 to 10 watts, so I had 10 dB of gain. If I went from 1 to 100, I had 20 dB of gain. If I went 1 to 1,000, I have 30 dB of gain. Now you're starting to see the power of the dB. If I had 1 to 1,000,000 watts, how many dB of gain would I have? The point is, the ratio is tremendous. In the last example, the ratio is 1,000 to 1, but I can write that with the digits 30 dB. Let's look at this another way. I have a little watt meter here, and notice I have 1 watt. I pass the 1 watt through a amplifier that gives me 10 dB of gain. So I have 10 watts. Let's pass that through another 10 dB gain amplifier, and I have 100 watts. Now you're starting to see the power of the dB. If I had an earthquake that was 1 on the Richter scale, and you had an earthquake that was a 2 on the Richter scale, you would have 10 times the earthquake I had, even though there's only a change of 1 digit on the Richter. Well, here, each time we have a 10 dB change. So while the power ratio between 0 and 10 is the same as between 10 and 20, because I started out with more, when I got my second 10 dB of gain, I got a lot more out of that, didn't I? Just remember, 10 dB more is 10 times the power. That's gain. I would write that as 10 dB or plus 10 dB or 10 dB gain. If my 10 dB is less, that's 1/10 the power, that's a loss. I would write that as minus 10 dB or 10 dB loss. And to review again, if I go from 100 down to 10, I've lost 10 dB. If I go from 10 to 1 watt, I have another 10 dB. To put it another way, if I go from 100 watts to 1 watt, the loss is 20 dB. It's the same with gains and losses. That's my point. Now let me show you something. Let's say this graph over here is no longer watt meters. It's not watts. It's power ratio. Let's say I start out with a 50 watt radio and I feed it into a cheap little amp and I get 100 watts. My power ratio is 2. That goes right there. Let's say I have 100 watts and I pass it through a cable and I lose half my power. So I had 100, now I have 50. That's also a ratio of 2, but that's a loss. But it goes at the same point on the graph, because I'm using the same formula for gain and loss. So let's move on to this. This is a chart. And over here is the power gain or loss, the ratio. And here is the dB scale. So as you can see, if I have 10 dB of gain, I get 10 times the power. If I have 9 dB of gain, I get 8 times the power. 6 dB, I get 4 times. 3 dB, I get 2 times the power. Now, you'll notice that this is the only one that is an exact number, other than 10. It's important to understand, I actually rounded this. The real number for 3 dB is 1.9935. The reason I corrected it to 2 is I want you to always remember 3 dB is twice the power, or 3 dB is half the power. The only number here that is guaranteed accurate is 10 dB really is 10 times the power. These others, there's a slight error in them, although it's not very great. If you were at 9 dB and you added 1 more dB, well, you would take 7.94 times the power factor for 1 dB, and it comes out to 10. Actually, it comes out to 10.0044. But again, like I said, there are little rounding errors going on here. So it's way better if you commit to memory that 3 dB is twice the power, 6 dB is 4 times the power, 9 dB is 8 times the power, 10 dB is 10 times the power. Now, one other thing here is, what about loss? What if we were measuring dB loss for power gain. That's where these numbers come in. 10 dB is 10 times the power, or if it's a loss, it's 1/10 the power. 9 dB is 8 times the power, or if it's 9 dB loss, it's 1/8 power. 6 dB is either 4 times the power, or 1/4 the power if it's a loss, on down the line. Now you notice over here, I put these two decimal numbers in, because 1/158, 1/126, my brain can't use that. So I commit these two to memory, along with these other numbers. However, I'm not telling you to commit all of this to memory. Here's another little secret to the dB. In your brain, work it out over and over so that you know that 10 dB is 10 times the power as a gain, or 1/10 the power as a loss. Once you get that memorized or learned or burned into your brain, work on 3 dB being twice the power or half the power. You can try to remember these two, but I wouldn't worry about it. In fact, I'd make a little wallet card just like this one here. The point is, you want to know that 10 dB is 10 times the power or 1/10 the power. 3 dB is twice the power or half the power. And you don't really have to remember it, but you might write these two down as well. You can do almost everything with these four numbers. Let me explain. I buy an amplifier for my 2-meter radio. They claim 150 watts out maximum. Drive level is 3 to 6 watts. And whatever I put in it, provided I stay below 6 watts or at 6 watts, I'll get 14 dB of gain. How much power do I get if I put 5 watts in? Well, if you're really good at math, you can rearrange this formula and it'll tell you. But let's assume neither one of us is that good at math. Let's copy the specs of the amp up here in this corner. And let's ask ourselves, how can we define, with what we know, what 14 dB of gain is? And let's not forget our little wallet card. And remember, we've committed to memory that 10 dB is 10 times the power. Well, 14 is 10 dB plus 3 dB plus 1. So 5 watts is going to hit the 10 dB and become 50. Then the 50 will hit the 3 dB, and that's double, right? So that's 100 watts. The last dB is a 1.26 power ratio. So we multiply 100 times 1.26, we get 126 watts. Does that really work? Without using the formula, can we really get away with this? Well, let's find out. I said 126 watts out for 5 watts in. I put those numbers in. I get a ratio of 25.2. I take the base 10 log of 25.2. I multiply it times 10. I have just confirmed that I do have 14 dB of gain. And you can do it with any numbers. Let me show you. What if I had 17 dB gain? Well, 17 dB is 10 plus 3 plus 3 plus 1. Remember my little wallet card here. I do it again. 5 into the 10 dB. Then 3 dB doubles the power. Then 3 dB doubles the power again. And then 1 dB increases it by 1.26. Another way to look at it is 17 dB is 10 dB plus 6 plus 1. If we can remember that 6 dB is double of a double, which is 4 times, we can say 5 watts plus 10 dB is 50. Now, 6 dB is going to increase that 4 times. Then we add our 1 dB, and we get the same number. The point is, drill it into your mind. The idea of 10 dB is 10 times or 1/10, and another 10 dB, you just repeat the process. Go all the way up to 150 dB if you want to. It would be good if you could remember 6 dB is 4 times or 1/4. You definitely have to remember that 3 dB is twice the power or half the power. And these last two are kind of optional. You don't use them that often. Notice now you're doing all this work with dB and you're not doing any logarithms and you don't need a scientific calculator. One last little item. What if you had the most lossless cable? You put 100 watts into it. At the other end, you get 100 watts out. 100 divided by 100 is 1. The base 10 log of 1 is 0. 0 times 10 is 0. So you have 0 dB. 0 dB means you have no change. It does not mean you have nothing. It means nothing has changed. So dBs indicate the amount of change. If you have no change, by the way, we often say 0 dB is unity gain. Well, you could really say unity loss as well. But just keep it in your mind that 0 dB does not mean nothing. It just means nothing has changed. That's it for this time. Now, next time I'll talk about the dBm, and I'll show you that you can actually use the dBm to measure quantities and express them easily. And it's a little bit different from dB, but you've got to understand dB before you get into dBm. Anyway, that's in DCL 093 Part 2, which you'll find on my YouTube channel as a separate video. Thanks very much for watching. I hope this was well worth your time. And I wish you the best of luck in your ham radio exam if that's what you're studying for.